Hey y'all, it's Mr. Boyden, your personal math teacher, back at it again, and here we are, so let's do this. Here's an outline of what we're going to talk about today with least squares regression and with residual plots, which we introduced both of those in the previous video. And so if you're looking for the very basic introduction to these things, go ahead and watch the video right before this one. But here's the things we're going to talk about today. We're going to talk about regression lines, okay, and we got those on here. Before I go and say anything more about that, I want to zoom in and get this notation down and give you a chance to get it. Okay, this right here, the way we say that is y hat. Okay, and the significance of the hat is saying that it represents a prediction. And it is important that you use that symbol and that you know that symbol, you know that it's called y hat, and that you understand that it's called a prediction. Okay, and in class, that's how we're going to talk about it. If you go, and especially if you're going in any kind of science field or in any kind of medical or bio field or whatever, you're going to be using statistics, and they will expect that you know that phrasing. Okay, and they will call it that in college as well. Okay, so that's y hat. These two formats of the line, they are essentially the same thing. Okay, now the textbook we use has the notation on the left. Sometimes textbooks or exams will have the notation on the right. It's important that you realize that they're the same thing. Okay, and let me just highlight that for you. So like this value, see how it's just a constant, it's by itself? That's the same thing. And over here, you see how there's a variable next to x, like b sub 1 is next to x, here b is next to x. Those are the same value. Okay, so don't get hung up like, oh, but is it b naught or b1 or b or a or no, hold on. Like one of them is next to x, that one is the slope. Okay, so slope. And one of them is alone, it's a constant, and that represents the y-intercept. So if you ever start to get overwhelmed with linear regression, just pause and say, wait a minute. This right here is basically the same thing as y equals mx plus b. It's just in a different order. So that's exactly what you learn in algebra, okay? All right. Least squares regression, we're going to learn a little bit more about this in a minute. That is how the calculator picks the line. Sometimes teachers will say, like, it's the line of best fit. We want to try to stay away from that. There's no such thing as the best line. Least squares is a method for finding a line, and it's the one, because it's an easily definable method, that's a good one to use, and that's the one that we often use in statistics. It's accepted, but who's to say what's best and what's not, okay? And what I'm talking about is you probably have had a teacher at some point who had you draw a scatter plot of something, or they gave you a scatter plot, and they say, hey, draw a line of best fit. You said, this is my line of best fit. And then a classmate says, well, my line of best fit is like this. And your teacher says, they're both best. Okay, wait a minute. Wait. The word best implies there can only be one. You can't have two different things that are the best. Okay, and that's one of the reasons that we don't like that. Not to mention, who's to say which one is better? I mean, it depends on what you're trying to do with it. So anyway, please, I'd like you to kind of remove that from your vocabulary, if you could, please. Okay. Residual, we talked about that last time. We showed the residual plot, actually. Here we're going to formalize that. So the residual, what is it? It is just the difference, also the distance, same thing, between an actual value that was measured and a value predicted by the regression line. So you may want to add this down in your notes, that it is an actual y value minus a predicted y value. I've also shown that in symbolic form over here. Okay, so y minus y hat. Okay, remember we saw in the video previously that if that value was negative, the point was below the line, and if the value was positive, it was above the line. Okay, residual plot, that's just when you graph all the residuals at the same time. We're going to talk about r squared and s a little bit later in the video, so don't worry about that, as well as regression to the mean. We're going to talk about that a little bit later in the video as well. At this time, please feel free to pause if you want to write stuff down, or if you need to go back and listen to anything again, that would be awesome. We're actually going to jump straight into an example today. Okay, so let's suppose we did an experiment in class where we recorded the length of our hand and the number of M&Ms that we can pick up with one hand, and we got the following equation from the least squares regression. Uh-oh, Mr. Boyden made a mistake. Do you see it? I definitely should have had a hat over the M&Ms right here. So M&M's hat. Okay, so that's based on knowing your hand size, the predicted number of M&Ms, or how many M&Ms we would predict you could pick up. And that's what a regression line really is for and what it's supposed to be used for. Okay. I think I skipped over one of these. I didn't say anything about extrapolation, did I? Okay. Anyway, so we have those. Let's go back for a second. I realize I totally missed extrapolation because that's the point of this example. So extrapolation is when we use the regression line, or we use our model, whatever it is, to make a prediction that's outside of the range of X values that were used to obtain the line. That sounds super fancy, so let's look at the examples below to make it make sense in like sort of a real context. So let's say that a giant whose hands are 2 feet long enters the classroom somehow. Probably has to stoop down to get in. How many M&Ms do we think that that person can pick up? Okay. One thing it didn't say about this, this was meant to be in inches, by the way. So did it say that? It didn't say that, but that is supposed to be in inches. So what we would do to figure this out is we would take that 2, convert that to 24 inches, and just plug it right in the equation. So 7.38 minus 19.2, and grab a calculator. Okay, and I got 157.9. Now we can't pick up a partial number of M&Ms, so I'm going to round that to, we're predicting that he can pick up, or she, or they can pick up 158 M&Ms. Good chance to work on your ampersands here today. Okay, now, why is that extrapolation? Well, think about how big your hands are. Okay, the length of your hand. So my length of my hand is, I don't know, it's maybe 8 inches or something like that. Okay, and so a really small person's hand might be 4 or 5 inches. A really big person's hand, I mean, like an NBA player, it could be as big as like a foot. So the values that were used to make this, though, of high schoolers is probably, I don't know, probably between 5 and 8 inches. So would we expect the pattern that we found for people with hands of this size to still apply for people whose hands are 2 feet long? I don't know. Maybe. It's possible, but we should be careful just saying, oh yeah, a giant is definitely going to be around 158, because we don't know if that's going to hold up. Let me show you an example that's even more obvious. Let's say we find a mouse inside the classroom. We say, ooh, let's see how many M&Ms a mouse can pick up. Okay, so the mouse has, we grab the mouse, we say, okay, we're going to measure your little paw there, little mousey, and little mousey has paws of 0.32 inches. So we plug that in our equation. So 7.38 times 0.32 minus 19.2. Now, aside from the obvious issue here that a mouse is not a human, I totally get that. But I didn't have like an infant or whatever to use. So let's use the mouse. So 7.38 times 0.32 minus 19.2. And the mathematics says that the mouse can pick up about negative 17 M&Ms. Okay, and this is why we have to be aware of extrapolation, because in this second example down here, it's obvious that that's absurd. You cannot pick up a negative number of M&Ms, but this value might be absurd, it might not be, and we don't know that. So we have to be careful making predictions when they're well outside of the range of the data, because this pattern we know holds up for people who are hand size between 5 and 8 inches or whatever it was. But anywhere beyond that, we're not really sure. And that's what extrapolation means. Extrapolation isn't always bad. In fact, sometimes you have to extrapolate. Like, for example, when they predict how tall you're going to be. They're making an extrapolation about using your heights over the last couple of years to, for a kid, to say how tall they're going to be in the future. And so that is an extrapolation. That's also why it's often wrong. I mean, I can't even tell you when I was growing up how many boys were like, yeah, the doctor said I'm going to be 6'8". Well, we look around high school, everybody's 6 feet tall. I mean, what the heck? You get to the 10-year reunion, there's nobody there that's 6'8". Well, the doctor said, well, the doctors are doing their best, but they are extrapolating. So apparently in my town, people were really big kids, and doctors thought they were going to be really big. But that means it may not be right. Okay, that's the whole idea of extrapolation. All right, let's talk a little bit more about least squares regression and what it is, and why is it called least squares. So here's an example that we can use, and this is just an online application I found, and they call it best fit. Oh my gosh, of course they do. It's least squares is what it actually does though, and here's how we know that. We can put a line on here, and I'm gonna just make a guess, okay, what I think a line would be. So I don't know, somewhere in here maybe that's the best fit or whatever, so to speak. I'm being kind of tongue-in-cheek here, right? I look at the residuals. Okay, well I got a big residual there. That's not so good. And I'm going to add on the squared residuals. So you see how it turned each of those residuals into the side length of a square? The least squares line, what it's trying to do is it's trying to minimize the total area of those squares. So like, for example, this is a big area right here. That's why correlation is not very resistant, because that's getting squared and it becomes a really big square when it's a bigger residual. So maybe I play with this, say, could I make it a little smaller? I can make that big square smaller, but it makes a lot of these other squares bigger. And so somewhere in there, there's the optimal, and I can go, obviously that's too far, and I can go down here, and there is an optimal way to do it though. And so let's put that in. And they're saying that right down there is where that optimal is. So it looks like my slope was pretty close. They're saying that's the optimized one is really close to that. Okay. And all that's saying is it just makes those squares as small as they could possibly be. And that's what least squares regression is. And that's what it does. Okay. We're going to look again at a couple more residual plots. Okay, so on the left here we have a graph. On the right we have the residual plot for it. Again, I want to remind you that what a residual plot is showing us, like this point is that far above the line, which means its residual is that size. So whatever that distance is, that's the residual of that point, and it's positive. This point's below, okay, this point's below, and there they are, there and there. That's why they're below, and they have a negative residual. Notice down here the residuals go negative. Okay, that's all it says. Let's look at the next one. This is a residual plot, not a scatter plot. So the question is, what does this residual plot tell you about the data? Okay, well look at that. There's a clear pattern here, isn't there? Okay, this means that the actual graph was not linear. It doesn't say anything about whether it had a positive or negative association. We have no idea. In fact, let me show you how I know that it doesn't do that. The data could have looked like this, and then the trend line's going like this. That would produce that residual plot. The data could be going like this, and it's a negative correlation, and the residual plot would have looked like that as well. So some people are like, oh, that means it's definitely, or it has, it's not going up or down. No, we actually don't know that from the residual plot, but what this one is telling us is it is not linear, definitely not. And that's one of the things a residual plot can tell you really rapidly, is that it's definitely not linear. Okay, what does this one tell us? Not a lot. Possible outliers, well, probably not. They're not. This one up here on this graph looks like it's way outside the pattern. But if you look, like these points in here are not that far below in terms of their residuals. So actually, what it might be doing is it might be telling us that this is probably not an outlier. I mean, it's definitely an extreme value, but it's not so extreme that we'd say like, oh, it's way different than the rest. Looking at the residual plot, it's kind of in there. In fact, this one, which is this point, is equally extreme in terms of how far it is from the line. So that might be a new way of thinking about that maybe you hadn't thought about before. Okay, and here's to summarize that. A regression model is appropriate when we see no curved pattern in the residual plot. So a residual plot, that's one of the things it can be used for, is to tell us if it even makes sense to use a linear pattern, which means we could use the least squares regression line, where we could use that process in the calculator. Okay. By the way, your calculator doesn't know of another way to find a regression line for linear. Least squares is all it has. That's the one that it does, because it's the one in statistics we've agreed upon, because it's a process that's easy to nail down. We'll see that process in a second. Let's talk about one other thing first. Okay, and a lot of this is just definitions. Okay, we need to know what S is. We need to know what R squared is. S is the standard deviation of the residuals. Hold up. each of these residuals has a value, right? Like over here, like this one's like a -2, and this one's like a -7 or whatever, and this one's like a 1. Okay, it's all those values put in a list, and then you find the standard deviation of those, and it'll do that for you when you do regression. Okay, the calculator will. So that's the standard deviation of the residuals. Now remember, standard deviation is a typical distance of a value normally from the mean, but mean in this case means from the predicted value. So what's a typical distance from the predicted value? Predicted value, by the way, that's another way of saying the line. The line represents the predicted values. Okay, now what is r squared? R squared is what's called the coefficient of determination. Please write that term down. There is often a multiple choice question in AP that asks you about the coefficient of determination, and you need to know that that's r squared. Now, maybe that gives us an opportunity right here to review for a second. What if it was not squared, if it was just r? Do you remember what it's called if it's just r? R is referring to the correlation coefficient. Okay, so r is correlation coefficient, r squared is coefficient of determination. It's a good idea to write that down. That's, in my mind, one of the hardest things in statistics, is just getting down all the symbols and all the vocab. The concepts are, at least for me, they were a little easier, but I sometimes would get so overwhelmed by all the different words and symbols. It's like, oh my gosh, why does it got to be so hard? But once you get it down, like anything in life, once you get it down, it's not that hard. Okay, no different than when you started writing sentences in first grade. It's pretty hard to write a good sentence. Now you're like, sentences? Are you serious? Of course I can do sentences. Of course. Okay, so what is r squared? According to AP, it tells us the percent reduction in the sum of squared residuals. Oh my gosh. Here's when you're asked a question, here's what it is usually asking for. It measures the extent to which the line accounts for variability in the response variable. Okay, and I want you to actually write that down. So you may need to pause the video here to buy yourself some time. So pause now. I'm not going to say anything important in the next minute here or whatever, a few seconds. So pause. And now you hit play and your notes look the way you want to. Let's keep rolling. Okay, let's do an example of these two things. All right, in my algebra class, the students measured the length of their feet, which we're calling the explanatory variable, and the length of their legs, which we're going to call the response variable. Then the students put the data into their TI Inspire, and they got the regression equation given below. Y hat equals 12.2 plus 1.015x, where x is the length of the feet. That's the explanatory. Okay, so I'm going to make a note here. That's feet. Length of feet. And the length of the legs is y, because that's the response. Okay. They were also told that r squared equals 0.989, and the measurements were done in centimeters. Okay, this is a classic test question. Interpret the values of s and r squared. I want to invite you to pause the video if you want to try to use what's on the screen here up above to try to answer those questions for yourself and then get some feedback. Then I'm going to put on the screen what are like the golden textbook answers that you would need to give for these. All right, if you hadn't had a chance to pause and you want to, do it now, because I'm about to put some answers up here on the screen for y'all. Okay, here they are. This is like the classic textbook response. So in this one, we're going to reference the value for s. So s being 4.11 tells us that leg length of students typically deviated. So leg length, it's referring to the response variable, right? Typically deviated, I'm saying it's a standard deviation, typical distance, 4.11 centimeters from the number predicted by the regression line. Guys, that's a classic textbook response. Let's look at the next one, r squared. It tells us that 98.9%, so I turned that into a percentage. Okay, 98.9% of the variability in leg length in the response variable is accounted for by the regression line. Okay, and notice response variable for r squared. Now I want to add one additional layer to this question. It's a concept that's not very hard, but that we haven't had a chance to practice together yet. So I'm going to add it up here, and the question simply is, what's r? We were given r squared, and so as you were probably hoping would be true, the way you find that is if r squared is 0.989, r will be the square root of 0.989. So I'm going to type that in my calculator. and I get 0.994. But not so fast. You remember in pre-calculus when your teacher, who possibly was me, said anytime you take a square root, it gives both a positive and negative answer, right? Like you got to put a little plus or minus in front of it. Uh-oh, so what does that have to do here? It means that we need to pause and ask ourselves, wait a minute, is the correlation positive or is it negative? Is this a graph which is going up and to the right or down and to the right? How would we know that? Let's look at the equation of the regression line. What's the slope? Remember, the slope is always the one that's with x, with the variable. So the slope is positive, and so in fact, our correlation coefficient is the positive version. Okay, now guys, that's how you find r. If you know r squared, take a square root to find r. If you know r, square it to find r squared. They do relate in that way, so luckily those symbols work the way they seem like they should, algebraically speaking. Let's do another example. Okay, in this example, we have a random sample of 11 high schools that were selected from the state of Washington. The percentage of students who are eligible for free or reduced lunch and the average SAT math score of each school were recorded. So there's the graph, and let's just interpret so we can understand in context what's going on here. It's basically showing that the higher the percentage of free and reduced lunch as we go to the right, the lower average SAT score. Again, suggesting that schools that have more families from affluent neighborhoods maybe have the resources to prepare for the SAT math test a little better, something like that. Okay, so there's our graph. Down below we have a residual plot. So let's double check. Does it look linear? Up here it looks linear. Do you see any curviness in the residual plot? Nope, looks pretty random to me. So I think that's okay, it is linear. And then, oh my, look at what we have over here. Okay, let's talk about this. This is what they call like a statistical computer output. So computer output. This is somewhat antiquated. Okay, it would be really unusual that you would actually use a piece of software that pumped this out. More than likely, AP does put these on their tests from time to time, and you do have to interpret them and use them. And so that's what we're going to look at right now is how does this stuff relate to what we already know. Some of that is going to be really obvious, right? So like, they say S equals right here. Well, yeah, we just learned what S is. That's the percentage of variability that's accounted for. Okay, R squared, or no, excuse me, the standard deviation of the residuals. R squared is the percentage it's accounted for. And look at that, they even gave R squared as a percentage. Okay, so it literally is the percentage of variability in foot length that's accounted for here. Okay, and so there's a couple other questions that we need to be able to answer from this. And so I want to show you how to think about that. So what are those questions? Let's answer them. First of all, is a linear model appropriate for these data? Yeah, definitely. Because there's no curviness in the residual plot is why we would say so. That's the reason. Okay. Find the correlation coefficient. Hold up. Correlation coefficient. Correlation coefficient. Which one was that? That's a vocab term. Guys, that's R. Okay. So we need to know what R is. We don't know what R is. We know what R squared is. R squared is 0.8529. So we're going to take a square root on both sides. Don't forget the decimal point. It looks like I wrote over the top of it. So square root of 0.8529. And I got 0.924 when I did that. But wait, is it positive or negative? There's two ways to know. The easiest one is if you have a graph, you go look at it and you say, is the slope positive or negative? Let's go look. Is that slope positive or negative? Ooh, it's negative. So that means my correlation coefficient is negative. I'm going to show you the other way to know as we're answering part C. They asked for the equation of the regression line. All right, hold up. Let me drag this down here so we can see a little better. They want the equation of the regression line. Yeah, we can do that. No problem. Okay, now, guys, when you see this computer output, I don't want to say that any of these numbers are meaningless because that's not a very nice thing to say. However, I do want to tell you that I've never seen a question that asks for any of these numbers, and I've never seen any of these numbers get used. Okay, and so if you just take those off your plate, those 6 values, that's half the numbers on here, and it makes it a lot easier to interpret after you realize that those are not going to do anything in this context. Okay, so get rid of those. Now, in order to write the equation of the regression line, then we would need to know what the slope and the y-intercept are. You see how right here they said this is the constant? Constant means it's the y-intercept. You see how this one relates to foot length? It's not a constant. That means it's the slope. In this example, we could probably see that anyway, because if you go back and look at the actual graph up above with the line on, you see how the, like up here it hits at like 560, 570? This is saying it's hitting at 577.9. It's telling you that y-intercept right there. And that -2, we can see that in the slope. See, it's a negative slope. Okay, so that's what that stuff is saying. So what we're predicting, so SAT math scores, so I'm going to write it like this. I'm going to write it as math hat, so the predicted math score is, now stats, for whatever reason, they like you to put the constant first. They put these in the order they're written. So they're going to go 577.9 minus 1.993, and they do percentage of free and reduced lunch. So I'm going to write this as percentage FRL. Okay, now in mathematics, we normally don't write words inside of equations unless it's a logarithm or something like that. In statistics, it's totally fine. Okay, you can write math hat and you can write percentage FRL in there, and it's understood that that's standing in for a value that you could plug in. Okay. So I said I was going to tell you another way how we would know that R was negative. R is negative because now that we realize this is the slope, negative slope means negative correlation coefficient. All right. D, by about how much do the actual SAT scores typically vary from the values predicted by the regression line? All right, guys, it's all about coding. Let's translate that. What are they asking us about? How far do they vary from the predicted values? Values predicted. The values predicted is the line. Guys, they're asking us about the residuals. That's what it is. How far are you away from the line? They're saying, what's the average, or the average distance of the residuals? That's the standard deviation of the residuals. That's right here. That's S. So this is 23.3 points because they're asking about scores. Okay. And interpret the slope. This is an easy one to get wrong. So first of all, the slope, oh wow, I've got the wrong thing, foot length. We're gonna roll with it. I don't know why they put I guess they made a typo, they put foot length in there. That's super weird. So for the slope, first of all, we need to know what the slope is. The slope is negative 1.993. Guys, I totally just noticed that says foot length, which is weird. I took these from the same problem. I guess the book made a typo is what I'm thinking is what happened there. So don't worry about the fact that this says foot length. Okay, so that's the slope. Here's what I want you to remember when you're going to interpret the slope. A couple things. First of all, remember that slope is rise over run. Okay, and I'm thinking like back to algebra class, right? And what does the y values in this question mean? It's not like a secret question. Look back at the graph. The y values are the math scores. Okay, so I'm just going to fill that in here. So this is math scores divided by percentage of free and reduced lunch. Okay, so what this is saying is, these go in, the fact that it's negative is saying these go in opposite directions. Like as the percentage of free and reduced lunch goes up, the math score goes down. Now, guys, it's not saying that it's like a 1-to-1. It's not saying that like the math score is always negative 1.993 times the free and reduced lunch, because we have a starting point. Okay, and that would make, and if that was true, it would make the values negative, or make the test scores negative. So what we want to say for our interpretation of the slope, we want to say for every additional percentage point of students who are on free and reduced lunch, and I'm going to color code that and write what I'm saying. It's saying that if this goes up by 1%, then this has to go down by the slope amount, which is down by, or I shouldn't put negative, it goes down by 1.993 on average. Okay, it's not exact, it's on average. So for every additional percentage point of students who are on free and reduced lunch at a school, we expect that on average, the SAT math scores, or the average, or yeah, the SAT math scores go down by about 1.993. Now, guys, you see how I'm being really like sort of soft and squishy in my writing here? So I'm saying we expect that on average they go down by about that much. Okay, now for AP stats, if you use, they call it deterministic language. If you say like for every percentage that free and reduced lunch goes up, the scores go down by 1.993. They're going to mark you down for that. It's not that it goes down by 1.993, it's that on average they go down by about that much, or that our line predicts that they will go down by about that much. So you have to use, I call it squishy, they call it non-deterministic language, tomato, potato, I mean, it's up to you, okay? But you don't want to say that it's exactly doing this. It's the exact same idea as we would never say the data are normally distributed. You have to say they are approximately normally distributed, same idea, okay? In that non-deterministic language. Okay. Last thing we're going to learn today, and we're going to do one example of it, is called regression to the mean. Okay, and I'm going to sort of parenthetically call this how they found the line before computers. Okay, so now with computers and calculators, you put in the data, you say beep, boop, beep, what's the line? And it says got you, and it spits out the line. And that's really, really wonderful, because as recently as like 50 years ago, that technology just didn't exist. Back then, people had to do everything by hand, and so they still want you to have the very basics of how that works. And so what I would like you to do now is first just write down the formulas up here. Okay, and I have some extra words if you want to pause and read them. That may be helpful, kind of read them like a textbook. I'm basically saying if you have the right information, then you can write the equation of the line. So the equation of the line is this, where b, which is the slope, is found by calculating this value, and the y-intercept, a, is found by calculating this value. Okay, so guys, I want you to pause the video and write that stuff down, because we're about to do an example. And you do need to write down. There's no way you're going to keep up with the way I'm talking, so pause. All right, let's do the example. We're going to go back to the 11 high schools in that previous example. Okay, so let's say the mean and standard deviation of the percentage of students on free and reduced lunch are 37.55 with a standard deviation of 26.37. Mean and standard deviation of the average SAT math scores are y bar equals 503.04 and S sub y, the standard deviation, 57.68. And they gave us the correlation coefficient of negative 0.9236. And then we were asked to, this is a classic question for like a multiple choice especially, find the equation of the least squares regression line. Guys, I want to remind you really quickly, I know we've talked about it before, but I would like to remind you though, of this symbol up here. You see how there's a thing going on top of the y? I want to remind you the way we say that is y bar. The significance of the bar is that it is the mean. Okay, where like a hat is a prediction, the bar means the mean. I know at first I was really confused in statistics. I'm like, wait, but a hat and a bar, those are similar, right? Like same thing basically. No, not at all. Bar is always a mean, hat is always a prediction. Okay, so be careful about that. Don't make the mistakes that I made. Do as I say, not as I did. All right? All right, let's do this question. And so guys, this, you just literally use your basic algebra skills to figure this out, and we plug in what we know. So what were we told here? We know the values for the first equation? Yes, we absolutely do. So I'm going to plug those in. B equals R, which they told us is negative 0.9236, multiplied by S sub y over S sub x, because we're given those, okay? And this is typical that AP would give these to you. So 57.68, and S sub x, so 26.37. By the way, not a coincidence that it's y on top and x on bottom. That's like rise over run with slope, right? Okay, so that's where that's coming from. So let's use our calculator. Let's figure out what that value is. Okay, and I got negative 2.02. Okay, let's see if I can do the next part of things. Can I find A? I don't know, let's find out. So A would be y bar. Do I know y bar? Yes, I do. There it is. Cool. So 503.04 plus, oh, excuse me, minus B. Okay, we just found B, so that's what we're going to plug in. So minus negative 2.02 multiplied by, according to this, x bar. Where's x bar? 37.55. And again, y'all, that's just going to be calculator time. Okay, so just take a moment and plug that in. Okay, and I got 578.9 when I did that. Okay, and it is going to be a little bit off compared to what we have above because there's some rounding in here, and that's pretty typical. When you have a little bit of rounding, your line will be just a little off, but AP understands that. They're not going to mark you down. Okay, now this is where it all comes together. The equation of the line, y hat. So y hat equals A, we just found that, 578.9 plus, except it's B is negative, so plus BX, so minus 2.02 X. Okay, so it's pretty typical that there's 1 to 2 questions about this on the multiple choice section of the AP exam, so that's what we want to look for. It's one that, and by the way, I didn't mention, you do get these formulas on a formula sheet for the exam. Okay, so you please don't spend time memorizing them. That's not a good use of your life. Like, life has a finite number of minutes to it, right? Let's not spend them on that. Okay, so you will get formulas for those, and so just staying calm, honestly, is one of the biggest keys to doing these correctly. You gotta stay calm and say, look, that's a lot of symbols. I get that, but they gave me a lot of values to plug in, and I know how to plug in values, and I get a calculator, so I'm gonna stay calm and I'm gonna get that. Guys, if you're still watching, thank you. Thank you for staying with the video, and for hopefully it was useful, hopefully it was enjoyable, and that's all for today. So I'll see you next time.